저는 일본의 리스트 고베센터의 요시오 오야나기 특임 자문님을 모시고 일본의 그 슈퍼컴 사례 도입 히스토리에 대해서 듣도록 하겠습니다. 사실 슈퍼컴이라고 하는 그 파워 능력은 한 나라의 과학기술의 경쟁력을 대표하고 있고요. 또 여러분이 그 능력을 어떻게 활용하느냐에 따라서 나라의 경쟁력이 좌우되겠죠. 자, 아시아에서 슈퍼컴퓨팅의 한 축을 담당하고 있는 일본의 사례를 우리가 좀 바라보면서 한국이 어떤 방향으로 나가야 될지 살펴보도록 하겠습니다. 자, 요시오 오나야기 특임 자문님을 앞으로 모시겠습니다. 박수로 환영해 주시기 바랍니다.
Well, thank you, Chairman. I couldn't understand what he was saying. So it is my great honor to give a talk at this conference. And I also thank the organizers to invite me to this conference in a very delicate political situation between Ilbon and Tehaminguk. So, but I would like to talk about the history of not only supercomputers but also computer itself. Well, the history starts nearly 100 years ago, before the Second World War. At that time, there were no computers, but only punch card system or punch card machines. And Japan imported, the first one came 1923. And it was mainly in a bank or census office or something like that. But the only university which introduced IBM punch card machine was Kobe University. That was just before the Second World War, 1941. And one professor promoted to use a punch card machine for businesses. But the Second World War started, and we could no longer import punch card machines from American companies. So Japan wanted to copy the machine. The next slide shows the current exhibit of Kobe University. This one is familiar for old people. It's a punch card machine by hand. But you will notice two big machines. It's a sorter. It's sorter card according to the punched holes. And the right one was original IBM sorter. And the left one is a copied one in Japan. Quite similar, except the hopper part. So it was one big effort of utilizing the so-called computers in Japanese society. So after the World War, scientists in universities wanted to use computers. But at that time, we were poor, and computer was so expensive to buy, especially a big one. So some universities introduced smaller machines, which they could afford. But some universities developed computers by themselves, by hand, in a sense. University of Tokyo Faculty of Engineering built TAC, Todai automatic computer. With Toshiba, it's a vacuum tube machine. And Osaka University also started to build a vacuum tube machine. And University of Tokyo Faculty of Science built a PC-1. It's a parametron computer. It takes a long time to explain what is parametron, but anyway, it's a handmade machine. And Kyoto University developed a transistor machine, not IC, it's a discrete transistor machine with Hitachi, and Tohoku University built NEC, with NEC, in collaboration with NEC, SENAC, it's also a parametron machine. And Keio University built a transistor machine. And those computers were built by hand, but it was heavily used in the campus. Oh, this is a photo of a PC-1 in University of Tokyo. It's a handmade computer, as you see. It's a handmade one. This is Professor Goto, a famous guy in this field. After some years, government started to organize a kind of authorized official computer centers in Japanese universities. First, Science of Council of Japan, it's an organization of scientists, recommended to introduce computers in Japan. And the University of Tokyo first proposed a budget to the government, and it was accepted. So they wanted to start a computer center, or large-scale computer center. And there were many discussions, but finally, the final candidates for the machine were three. Hitachi machine, that was still under development at that time, and IBM 7094. It was a very popular machine, but a little bit old at that time. And CDC 3600. It is many physicists were CDC lovers, and but it's a new one. I mean, it's a first. No CDC machine had been introduced in Japan. So there are very severe discussion, and committee decided to, to introduce a Japanese machine, high-tech 5020, a transistor machine. That means we rejected American computers like IBM or CDC or Univac or whatsoever. So computer center started in 65. This is old. So that is the computer of all times. Some of you may know. Main system and subsystem. And at that time, the computing was made by a card, paper card, not a credit card, it's a paper card. It was punched card, And this lady is combining the output of line printer and the original card deck. So this was made by hand. It's a computer center at the middle of 1960s. Soon after that, Japan organized 7 computer centers. Of course, the top one was Todai, but Tohoku, Kyoto, Osaka, Kyushu, Hokkaido, and Nagoya. So before 1971, 7 computers started. And those were not only for the universities. It's open to all teachers, staffs, and graduate students in Japan. All computers are open to all. That means, for instance, the professor in University of Tokyo can, of course, use University of Tokyo machine, but also Kyoto University if they like. And those machines, this is the first one, NEC, Fujitsu, and Hitachi in Tokyo. So those are all Japanese machines. So they were upgraded every 4 or 6 years. No. Yeah. So those are mainframes. And the computer develops from mainframes to supercomputers. You may know the first vector supercomputers called KREONE1, not first, but the most famous supercomputers. One of the most famous computers is KREONE1, which was installed in Los Alamos in '76. And that was we were in Japan and we heard the news that there were some so enormous computers called like supercomputers, but unfortunately they were out of scope, out of range, so we couldn't believe that one day we would be able to use such computers. But Japanese vendors, Hitachi, Fujitsu, NEC, tried to follow the Cray vector computers. So it is time-consuming to explain all the history of supercomputers, but there's a rough sketch of the development from 70s to the beginning of the current century. So we say generation 0, 1, 2, so it's every 5 years or something like that. There were top 2 lines were US trends, or 3 lines. Bottom are Japanese machines, Japanese vector machines. And the bottom line is those are the research project to develop new computers. Those are University of Tsukuba, which I used to belong. They were from PAX to PAX CS or CP PAX or something like that. And the bottom is the MITI, Ministry of International Trade Industry, now Ministry of METI. But anyway, they had a supercomputer project at that time. And then the real-world computing partnership was followed. And the 5th generation project, which you may know the name. So there are lots of competition and cooperation all over the world. We can summarize the trend as follows. The first half of the 80s, Japanese started to build the computers, but just following the American vector machines or comparable performance. But in the later half, the second half of 80s, Japanese vectors superseded Americans. So there came a trade conflict. So we'll explain later in events in NCAR or MIT universities. This first half of 90s, ASCII project or PACI project, PTAC, or any big work to supersede Japan. So the United States had a very aggressive policy, or started very aggressive policies. But in the first half of 2000, actually 2002, Earth simulator started, and it had a very high performance in the worldwide. And some years later, Blue Gene superseded that machine. And most recent, that means the second half of the 20s, there were K-computer development, and as I will explain later, it was, it was stopped in the middle and later. So this is kind of a graph of a top machine in every years. It started 50s, that was EDSAC or UNIVAC or the one. And this is rather old. The right hand is 2010. But anyway, there are Blue Gene or K-computer and the road. Anyway, the point is, so this curve, the top computer performance curve, is something like Moore's law. A little bit different of coefficient, but anyway, it's 300 times every 10 years or something like that. So we observe the Japanese vendors, Hitachi, Fujitsu, and NEC, focus on vector machines. And we exploited the power of vectorization. When I was a young researcher, the vector started, and I enjoyed using that. And vendors thought at that time, parallel machines, parallel computers were for specialized purposes, not for a general one. For instance, image processing or decoding or something like that. And most users, I mean application users, they are not trying to use the parallel machines in 80s. Especially the message passing, later MPI. At that time, there were machine-dependent message passing interfaces, but user found that kind of message passing very awkward. It's very hard to use. In terms of the software, it was the three companies provided very good vectorizing compilers. So the result is the users, Japanese users, were in a sense spoiled by that good vector machine and vector compilers. There was some effort of utilizing, to use the HPF efforts in the case of Earth simulator. And for the computer science side, of course, some computer scientists were interested in research of parallel processing. But it was for their own computer science interest and not used by practical application scientists. On the other hand, practical parallel computers, which can be used for real-world problems, were started by application users. That's the history history of Japan. There are some lists. QCD packs for lattice QCD. Numerical Winton, that's a parallel vector machine. Anyway, it's for fluid dynamics or atmospheric simulation. CP packs for computational physics. And GRAPE for astrophysics. Earth simulator for climate. Oh, no, sorry. NWT is a wind tunnel. It's a fluid dynamics, aerodynamics. And the Earth simulator is a climate, ocean, or earthquake. Those highly parallel machines were developed in the initiative of application users, not by computer scientists. That is the one characteristic of Japanese history of supercomputers. And also, supercomputers are used by commercial sector, in the commercial sector, industrial sectors. In the late 80s, there were some statistics. So in Japan, there were 10 Cray machines, but 8 were in commercial sectors. Or Hitachi machine has, there are Hitachi vector machines, 50 vector machines, but 9, among them 9 were used in commercial sectors. Fujitsu has a number of vector machines, but 23 out of 36 were used in commercial sectors. That is, of course, there are some supercomputers in universities and laboratories, but also the industry were very much interested in using the vector machines at that time. So I'll talk about the US-Japan trade conflict. Kathy is here, but I'm and for instance, the conflict began in '85 in the so-called Plaza Accord in New York Plaza Hotel, that kind of G5. And for instance, '85, SX2, it's an NEC vector machine, was adopted by NCAR, but after bidding, it was canceled by political reasons. And in '87, MIT decided to buy a Japanese supercomputer, maybe Fujitsu, so I don't know. But it was canceled in the same way. That was a US-Japan supercomputer trade conflict. There were so-called Super 301 Act. So in 89, US government decided to apply Super 301 Act. The full name is Omnibus Trade and Competitiveness Act of '88 to Japan, and identified 3 items, including supercomputers and the cars, and I don't know, I remember. So anyway, Washington pressured the Japanese government, governmental institutes like universities, laboratories, to purchase US supercomputers. So TI Tech, Tokyo Institute of Technology, bought ETA-10. That was a failure. And the Electrotechnical Laboratory bought it XMP. But on the other hand, US governmental institutions had no Japanese supercomputer at all, still now. So there are big progress in the United States. In the Blue Book, it's a subsidiary document for the budget proposal. It was announced a grand challenge. High-performance computing and supercommunications can solve big problems that they call grand challenges. And the High Computing Act of '91 was adopted, and some trade conflicts, as I explained. For instance, after that, there were Japan had some kind of supplementary budget to promote the economy after the burst of bubbling economy. So they had a special budget to buy supercomputers. And 6 out of 11 Japanese, 6 out of 11 computers installed was from United States, more than half. And in Europe, they started teraflops initiative. So this, you may know the so-called list of top 500, which started June '93. And this is the top 20 of the top 500 list. And you see a little bit small character, June 93 to November 2001. The orange block means Japanese machines, mainly installed within Japan, but some machines like this one, Canada, or there is a ECMWF or something like that. Anyway, the point is at this time frame, Japanese computer dominated the top area of the top 500 list. But US also had a strong political initiative to promote the supercomputers, a famous ASCII project. And PTAC, the Presidential Information Technology Advisory Council, proposed a very strong initiative to promote the information technology, including supercomputers. And PACI project is it's an NSF project. There are 2 PACI centers in the United States to promote the supercomputer environment in universities. And Petaflop's conference was actually started. So at that same time, Japan was doing what? 5-year plan for science and technology. There are always 5-year plans in Japan or China or something. And so the government stressed the importance of information technology. But they were thinking of mainly network, not supercomputers. So at that time, the government thought that the supercomputers were to be promoted according to the needs of each field. That means they do not want to build a supercomputer as a national project. But as I said, in 2002, Earth Simulator attained high performance, and it was a big news. And after that news, Japanese government, Information Science and Technology Committee of MEX is the Ministry of Education in a sense, discussing to promote how to promote computational sciences using supercomputers. So in the 20s, the ASCII also continued, and TeraGrid started, and Department of Defense also started HPC. It's a high productivity computer systems. And also the American Parliament, Congress adopted a High-End Computing Revitalization Act 2 times. And the EXA project started at that time. That is history of the second half of the 2000. Left column is Japanese events. K-computer started, developed, and also T2K started, and Tsubame started, as you know, and Fujitsu had a FX1 computer to JAXA. On the right hand is other than Japan, Cray or America, ASCII, but also China, Tianhe 1A, National University of Defense Technology, that's a Chinese top-ranking machine. So there are lots of events in the US, Europe, and China. So that is also top 20 in the top 500 list. You may notice that there are top 5 consecutive tables. Earth simulator was at the top, but it was downgraded, of course. And as compared to the former same graph, red-orange part is very small. And especially in the late, this area, no Japanese machines in the top 20 list. So that is the reason why we started to develop K computers. Yeah. So as I said, the government first thought IT was a network. That is true in one sense, but they shouldn't forget supercomputers or high-performance computers. So at that time, supercomputers are something like F1 race car. That's a hobby of computer scientists. So they can't pay for the hobby. But in 2005, there was a recommendation from a committee, which I was also a member. And according to the recommendation, government started to build next generation supercomputers in 2005. And RIKEN was the main developer. And there were discussions about what kind of architecture we should take. And 7 architectures were proposed. And also applications were discussed. And first idea was a hybrid computer of vector and scalar. But NEC retired, and the government changed, and there were a big event of governmental revitalization. This is Japan. The Japanese government unit proposed to shut down the next computer project. As the famous picture is next. This is a famous congresswoman, Lien Fan, who there was a meeting, working group, November 13th, Friday. The Friday, that's important. And the third working group. So the question was, why should it be number 1 in the world? Number 2 is not enough? That was the question of this lady. So as a result, the voting was abolish 1, postpone 5, and budget shrink 5, and the conclusion was freeze the project. Though I thought the project was almost dead. But actually it's revived, and it gained the top position in 2005. There are many achievements of K-computer. This is only an example. It's a UT heart, simulation of human heart from the protein dynamics, or lithium battery, lithium-ion battery. It's a big project. It's a car, automobile driving stability, or it's a tsunami, or something like that. So also, China was very eager to promote HPC, as I said. There are many lines, mainly 2 lines. Left one is the kind of army, military-related lines, mainly NUDT developed many computers. The right-hand side is commercial or spin out of academy group. There are lots of machines, and for some years, China monopolized the top position of the top 500 for some years. So this is the last years, the most recent years of the K was in the top position in two consecutive tables. But anyway, we also go down. And last table, K was the 20th. And it was retired last year. Last week. So we started the exascale machine, and the application was discussed, and the system architecture was designed. And there are many ideas, and this is one typical discussion table. The horizontal axis is the relative main memory capacity, and the y-axis is the relative bandwidth as to the flops. And of course, the best one is best, but it's always luxurious. And finally, as I see, the Fugaku position was something like that, rather high bandwidth, similar to K. Of course, memory is a little bit smaller. There are many walls for exascale: power, memory size, reliability, or programmability. And we were discussing very hardly. We had 25 meetings in 2 years. I was the chairman of that meeting. And the recommendation was a hierarchical development of supercomputers, and the leading machine, we should make leading machines. It was exascale machine toward 2020. Actually, it was 2021. So this is a TV news picture of the committee. So basic design of it was no accelerators. It's a very homogeneous machine. And the point is, peak performance is not our target. That's the point. And the power was 30 to 40 at most. The K was 12 megawatt. Electricity very expensive. And this is a system image, and named Fugaku. That means Fugaku is the old name of Mount Fuji. This is a famous Fugaku, one of the woodblock printing, 36 scenes of Fugaku. Oh, this is the logo of the Fugaku machine. This is Fugaku machine, the logo. I don't like it. The K computer logo was very artistic. And this is a chip design. It was also open, so I do not have time to talk about the details of that. The point is 68 cores plus 4 OS cores. And this is a picture of a chip and a blade, memory unit. And there is Satoshi Matsuoka, is the new director of this center. And this is the last week, August 30th, we had a shutdown ceremony. This is a TV, newspaper picture. So, in conclusion, we conclude something like that. Japan has manufactured vector supercomputer since 1977. The vector machines were designed as extension of mainframe, and the easiness of use was stressed. And vector machine, we kept vector machines, and some users started to use parallel machines. Yeah. So the users for the application users started the highly parallel machines, and it was used also industry, and we continue to develop supercomputers, and co-design and science-driven. That is our target. I think that's the end of my talk. Thank you for your attention.
Thank you very much.